we derived the equation J equal to sigma E. We understand that J and electric field both are vector quantities, and we also see that there is a sigma quantity there which is called conductivity. In reality, while J and electric field both are vectors, conductivity is usually a quantity called a tensor. For the time being though, for most of the analysis that we will study or do at this level, we are going to treat sigma as a scalar quantity. Starting from that, we will consider a cylindrical conductor like this. So this cylindrical conductor has two terminals as shown, and I have connected a battery to those two terminals, which is not shown in the diagram. And because there is a battery connected to the conductor, there is a current flow in this conductor, and that current flow is in this direction. So what we are saying is that I applied a potential difference of delta V here, and I did that by means of a cell or a battery, and then there is a current flow here, and that current flow we are going to analyze. The area of cross section of this conductor is A, the length of this cylinder is L. We define a quantity called resistivity, which is the inverse of conductivity, 1 by sigma. Therefore, this equation becomes I by A equal to 1 by rho, but then because we have applied a potential difference delta V here and the length of this conductor is L, using the concepts of electrostatics, we realize that this electric field in this direction is nothing but delta V divided by L. So I replace that E as delta V by L, 1 by rho is there, and so I end up rewriting that current I equal to delta V by this quantity. Now, if I look at this quantity in the denominator, we could say here's a cause and effect relationship. This quantity current is the effect, and it is the effect because there is a potential difference delta V here across the conductor. In other words, I am now saying this is the cause while the current is the effect. Once we start looking at it as a cause and effect relationship, then I realize the denominator here is going to resist the effect. In other words, if I maintain the same potential difference, then for the same potential difference, that is the same cause, if the denominator is more, the effect is less. Hence, this denominator is called resistance, which is nothing but resistance to the effect or the current. So we get the very well known equation, Ohm's law, and we are writing I equal to delta V by R. We have to understand though that this quantity or this equation I equal to delta V by R is really coming from the idea J equal to sigma E. Hence, we start recognizing this equation as Ohm's law as well as this equation. So both these are Ohm's law, J equal to sigma E as well as I equal to delta V by R, and the real way to look at this equation is always cause and effect. So here's the effect, which is the electric current, the flow of electric charges, and here's the cause, which is the potential difference. So given this equation, we will reconsider that R. We said this whole denominator is resistance, so R is now defined as rho L by A, where rho is the property of the given material, L and A are the geometric dimensions or the geometry of the conductor. Hence, resistance of a material depends on fundamentally two aspects. The first aspect is the resistivity of the material, in other words, the nature of the material. So copper will have a different resistivity, aluminum will have a different resistivity, mica in turn will have a different resistivity. On the other hand, you've got L and A, which are nothing but the geometric dimensions of the conductor. So we understand R is rho L over A, the SI unit of resistance is ohms, which is denoted by this Greek letter, and it is named after the great scientist Ohm. So resistance is always measured in ohms, and therefore this also leads us to conclude that the SI unit of resistivity will be ohm meter. Now we will understand the meaning of L and A. L is the dimension along which the current flows, whatever that dimension is. You may want to call it thickness, you may want to call it length, breadth, height, or whatever. The point is that those names are immaterial. Whenever we discuss a problem of electricity and resistances, we have to take that dimension of the conductor along which the current flows. And then A is the area of cross section perpendicular to current flow. Given these ideas, we will now start studying resistors and circuits containing resistors in detail. So we can now imagine a situation where you would have different combinations of resistors. For example, the first type of combinations is resistors in series. And as you can see in this diagram, there are two terminals here. I'm going to name them A and B. And between these two terminals A and B, I have placed three resistors like that in a row. Now, we immediately visually realize by visual inspection that these three resistors are in series. Now, in this particular case, of course, it's very obvious that they are in series. Visual inspection is playing a decisive role here. You can immediately realize that these three resistors are in series. But it is not every time easy, or it is not even possible every time just by inspecting the circuit visually to determine whether the resistors there are in series or in parallel. Since we cannot rely solely on the visual inspection of the circuit, we also have to come up with some deeper understanding, some deeper connection of series combination of resistors. And then we realize here, suppose I connect a battery here across A and B, then that battery or that cell will send a current I like this, let's say. So let's say that terminal A was connected to the positive part of the battery. So if a current I starts flowing here, enters that circuit here, then we realize resistance cannot eat up or create the current. Usually what happens is that students start thinking that resistors diminish the current or resistors change or reduce the current. Resistors do reduce the current, yes, but they don't reduce the current while the current is flowing through them. In other words, this current, while it is I here, it doesn't become less than I when it crosses the resistance. The current cannot change like that. The simple reason is you cannot create or destroy charges. So, if there are 5 coulomb per second flowing before the resistor, and if you now say there are only 3 coulomb per second flowing out, so then we have to account for 2 coulomb per second charges. Where did they go? We know that you cannot destroy them, and we certainly know that you cannot create them. In other words, if 5 coulomb per second are entering here, what must go out is also 5 coulomb per second. Hence, the current here which enters resistor R1 is still the same when it leaves, because you cannot destroy the charges. Now, this idea that current continues to go like that, so by the same logic, the same current is now here, and by same logic, the same current enters terminal B. As I was saying, it is absolutely wrong to say that current I enters here, but then current less than I arises here. That violates the conservation of charge principle, which is one of the most fundamental principles of the universe. So, what is the resistance doing then in this circuit? And the answer is this. Suppose I connect only one resistance R1, then this circuit will draw a different current from the cell. So imagine that I am connecting the same battery. I have only the one battery only, and I am going to use that battery repeatedly. So if I connect that battery between terminals A and B, and suppose I use only resistance R1, then that resistance will draw out, or in other words, now in that case the battery will send a different current through this circuit. If I connect another resistance R2 here like this, and just R1 and R2, then the current I itself which is coming from the battery will be different. On the other hand, if I connect one more resistance there, then again the current I which is coming from the battery will be different. In other words, this value of current I would be different depending on how many resistors you are placing here and what is the value of those resistors. So what is happening that when you place more and more resistors there, the current which is coming out of the battery itself is different, or itself would be less. This is a most important idea, that the current coming out of the battery itself changes when you put different resistors or when you change the circuit resistances. So this immediately tells us that it's not like the current comes out of the battery here and then it reduces and by that time it goes to the cell. You could even imagine a situation where there is no current entering the negative terminal of the cell because you kept on adding more and more resistors there, which is certainly very wrong. So we realize that if I keep changing the resistors in the circuit, the current which is coming from the battery, that itself changes. So coming back to this idea, one of our goal is to have a way to understand the series combination apart from visual inspection. And thus we now conclude that one of the very important features or characteristics of series combination is this: current through each resistor is same. So whenever we are facing a situation where visual inspection doesn't help us immediately to determine whether the combination is series or parallel, we have to ask ourselves, is the current through each resistor same? And then that will help us in determining whether the given combination is series or not. So having understood that, now our goal is to replace these three resistors with a single equivalent or effective resistor. Now when we use the word equivalent or effective, obviously that means the current which is entering this circuit must remain same. So if I have connected a battery between A and B, and then if I replace these three resistors with a single resistor, then that single resistor should not change the current I. That means the current I should remain same. It's just that I am replacing these three with a single resistance. How much is that single effective resistance, or how much is that equivalent resistance of this combination? So in order to do this calculation, I am going to define few more points on this branch. One point is this, I am going to call that point C. One point is this, I am going to call that point D. And then I realize I can write VA minus VB mathematically as VA minus VC plus VC minus VD plus VD minus VB, which is what I have written there. So all I am saying is the total potential difference is the sum of individual potential differences. So what is that delta V then? But then I can use Ohm's law for VA minus VC here. So now according to Ohm's law, delta V is equal to IR. Hence this potential difference AC is IR1. Then by again Ohm's law, VC minus VD is delta V between C and D, which is IR2, and that last potential difference is IR3. So we are now having delta V as that, but we know that we want to replace this whole combination with a single resistance R net. Hence, delta V can in turn be written as I times R net, and thus we get the series combination is always given by R1 plus R2 plus R3, and now you can generalize this result to any number of resistors. So the net resistance of a series combination is this much. The next type of combination we are going to look at is resistors in parallel. Again, if you look at this combination, it's very obvious that between terminals A and B, I have connected these three resistors parallel because visual inspection immediately tells us that they are parallel. Once again, the issue arises that can I have a different way, or can I have one more way which is a deeper one than just visual inspection, and which will also tell me or help me in determining whether the given combination is parallel or not. So now I will again send a current I by connecting a battery. So I have connected a battery between A and B. A is connected to positive terminal. So there is a current I coming there. This current I will now split at this particular point, and it will go as I1, I2 and I3. We know now this current is I1, this current is I2, and this current is I3. So basically what we are saying, whatever the current is coming from the battery, that current splits in three parts, I1, I2, I3, and then those currents reconstitute here to give you the same current I again. Then I realize what will be the potential difference across this resistance. But then one end of this resistance is directly connected to A, and the other end of that resistor is directly connected to B. That means the potential difference across R1 is again VAB or VA minus VB. By the same logic, potential difference across R2 is also VA minus VB, and thus we conclude a very important that potential difference is same across each resistor when the resistors are in parallel. So this is a very important or very crucial feature of parallel combination, that the potential difference across each resistor must be same. Therefore, we can now write again using Ohm's law, VA minus VB could be I1 R1, because that resistance R1 also has same potential difference, but it also could be written as I2 R2, again using Ohm's law, or it can also be written as I3 R3, again using Ohm's law. Then we had begun the discussion saying that there is a current I which enters the circuit here, and that current splits in three parts, I1 plus I2 plus I3. So this line here is actually a conclusion, or is a statement of charge conservation. So whatever current I that is entering there, it must be splitting in three, and charge conservation gives you this. So I'll replace I as delta V by R net, because we want to replace this combination with a single equivalent resistance. Again using Ohm's law and these relations, delta V by R1 is I1, I2 is delta V by R2, and I3 is delta V by R3. So we got that, and thus we get the effective parallel resistance of the circuit is this. You can generalize the result for any number of resistors as shown. Let us understand one very important thing here, and this is another place where a lot of students make mistakes. When we do parallel combination analysis, we have to realize that the left hand side we get is to be inverted. So you will do 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4, and then you do that for whatever number of resistors you have there. But what happens is that in the middle of the exam, students tend to forget that quantity that you have obtained by doing this kind of addition, that quantity has to be inverted, because this is how the formula is. And once we kind of understand that, and we are careful enough not to forget the inversion of this quantity, the reciprocal of this quantity, then there will not be any mistakes in the exams for this kind of problems.